Venus, our closest planetary neighbor and our sister world. Similar in size to the Earth, but about 40 million kilometers closer in orbit to the Sun. The second planet of our solar system has long been the source of stories, myths, and legends. In more recent times, however, we've gone beyond seeing just that bright circle close to the Sun at the start and the end of the day. Beginning at the height of the Cold War, numerous robotic missions have been sent to Venus to observe, orbit, and in some cases, even land. And, using technology that sees in not only the visible light but also in the infrared, ultraviolet, and radio spectra, what we have found is a world that is different to Earth in almost every way imaginable. If it were you, would you be curious enough to step onto this scorching and mysterious planet? Hello, and welcome to our cosmic journey. Join us as we take a journey to the star of the morning and the evening, using technology both old and new to uncover the secrets of Venus, and descending through its thick atmosphere to arrive at the surface of our closest companion. As the second brightest object in the night sky, and also the closest barring the moon in terms of distance, sometimes, Venus has always attracted attention from those who would gaze up at the heavens. But even today, interplanetary travel is hard, and at the height of the Cold War, it was even harder. Of the first 15 missions launched to explore Venus between 1961 and 1967, only 3 were classified as successes in terms of fulfilling their specific objectives: Mariner 2 and 5 from NASA, and Venera 4 from the Soviet NPO Lavochkin. Hello there. Let's continue our journey of discovery to Venus together. Successful atmospheric entries with Venera 4, 5, and 6 soon followed, and, in late 1970, the USSR finally passed a massive milestone with Venera 7, the first space probe to land on the surface of another world and last long enough to send back information about it. Let's now take a journey together with that same spacecraft, descending through what was found to be the many layers of the Venusian atmosphere that it found, and finally arrive on the surface. Still drifting through space, Venera turns towards Venus. As it begins its descent onto the planet, Venus's upper atmosphere lies before it, extending from the fringes of space at around 250 kilometers above the surface, and down to around 60 kilometers above it. Here, it sees nothing but a thin haze. 99% of Venus's atmosphere by mass lies below this point. This makes Venera's descent through this layer easy enough, in very much the same way as our own atmosphere would be at similar altitudes. But Venus's upper atmosphere's chemical composition could not be more different, a sign of things to come as we and Venera descend further. Instead of a majority of nitrogen and oxygen as on Earth, we begin to pick up traces of carbon dioxide. It's not enough to cause significant effects on temperature at this altitude, but it's significant as a marker of what lies beneath. Other than the difference in chemistry, however, at this altitude the atmosphere behaves roughly the same as that of our home planet at similar altitudes, with vast temperature differences between day and night. Highs of -37 degrees Celsius to lows of -143 degrees Celsius. For Venera, this is the easy part. An interesting sideshow to the noticeable presence of carbon dioxide is the presence of some oxygen atoms, which emit infrared radiation that can be seen by telescopes and spacecraft. In this picture taken by the Venus Express orbiter in the infrared wavelength, the blue is the air glow caused by the oxygen high in the Venusian atmosphere. As Venera moves downward through the layers, it comes to the main visible cloud deck of Venus at around 60 kilometers from the surface. The thick, dull yellow that we associate with pictures in visible light is almost entirely because of this cloud deck, terminating at approximately 40 kilometers from the ground. In this part of the atmosphere, ultraviolet radiation from the sun breaks up carbon dioxide into carbon monoxide and single oxygen atoms. These single atoms then easily react with sulfur dioxide and water vapor, two other trace compounds in the Venusian atmosphere, to produce the clouds of sulfuric acid that we see. This is the calm before the storm, the relatively temperate region before the real hell that Venera must soon enter. As you can immediately tell, the surface of Venus cannot be seen through the planet's thick cloud cover, so Venera will have to go in blind. That same cover reflects around 3/4 of the sunlight that hits Venus, as the ice crystals formed from the sulfuric acid that floats in the atmosphere are extremely reflective. This reflectivity goes a long way towards explaining how bright Venus looks, both to satellites going by and to observers here on Earth. Remember, it's the second brightest object in the night sky. When we look at those mustard yellow clouds in the visible spectrum, they appear thick and obscuring, revealing little of what lies beneath. However, we have an advantage that Venera did not possess: infrared sensor technology. If you enjoyed this video, don't forget to like and subscribe to support our channel. In the infrared spectrum, things look a lot different. This image taken by the JAXA spacecraft. Akatsuki throws things into much sharper relief, showing clear, light and dark spots and bands wrapping around Venus's atmosphere. And here is where we see the thick carbon dioxide composition of the atmosphere very clearly indeed. Carbon dioxide is an effective greenhouse gas, trapping the heat that arrives from the sun, resulting in an incredibly high surface and atmospheric temperature. Under the scope of infrared observation, this becomes very apparent as the entire surface glows under the heat generated by the thick layer of carbon dioxide. The dark patches and stripes are the previously mentioned clouds of sulfuric acid, and we can see them high above the much brighter, thick and hot carbon dioxide layer near the surface. Can you imagine what Venera would experience as it travels through this hell? Sulfuric acid assaults its outer casing relentlessly. Winds blow at 100 meters per second, 60 times the rotation speed of the planet, fast enough to circumnavigate the planet in just 4 days. The temperature, which at an altitude of 50 to 55 kilometers is anywhere between 25 to 75 degrees Celsius, sharply rises, reaching blistering levels. Surface air pressure on Venus is 75 to 100 times what you'd find on Earth. Comparably, it's like having an entire car sitting on your thumbnail. As Venera descends further, however, even weirder conditions can be found. Once Venera passes through the bottom of the sulfuric acid cloud deck, it arrives in clear air once again. But things here are strange. The pressure here is now so great, it's starting to have an effect on the carbon dioxide in the atmosphere. The density of carbon dioxide at this level is so high that it no longer acts as a gas, but more as a kind of supercritical fluid. A state of matter somewhere between liquid and gas where a substance takes on some of the characteristics of both. The wind has slowed down here after the baffling, fast speeds of the upper clouds. The atmosphere below is so thick that winds blow at little more than 5 kilometers per hour. It would feel like wading through water with a slow but inexorable current, albeit in a river that is 464 degrees Celsius, hot enough to melt lead. But what can modern technology tell us of these layers? To further illustrate the vast heat at this altitude level on Venus, let's look at a picture of the lower atmosphere of Venus taken in the near-infrared range, a wavelength of 2.3 micrometers, by the Galileo satellite, 8. The red-hot areas of the lower atmosphere are very clearly visible, as are the darker patches caused by the clouds of sulfuric acid higher in the atmosphere. The lower reaches of the Venusian atmosphere are incredibly hot, and there are distinct layers of that atmosphere, different in both temperature and composition. To further demonstrate the differences between the atmospheric layers of Venus, let's now have a look at the layers we've seen so far under ultraviolet light. While the images, again, from the JAXA Akatsuki spacecraft, taken in the 283 and 365 nanometer wavelengths, do not show as much contrast in color and brightness as the infrared images, they do show more variance than ones viewed in visible light. The areas of darkness and blotchiness of the cloud layers indicate the ultraviolet light is being absorbed rather than reflected. But exactly what chemical, or combination of chemicals, causes this absorption is still a matter of debate among the astronomy community. Clearly, there are elements and compounds of the Venusian atmosphere that still evade our attempts to discover and categorize them. And on the subject of Venus's atmosphere-defying explanation, here's a look at Venus's poles in infrared. Notice anything strange about them? Present at both Venus's north and south poles are large polar vortexes, about the size of Europe, whipped up by those 100 meters per second winds. What's really weird, though, is that they each have not just one central eye, but two, and scientists are still not quite sure why. Venus's complex, highly variable polar vortexes are extremely hard to model as they can change on timescales of less than 24 hours, making them quite the mystery. But once it was past the enigmatic atmosphere, what did Venera see down there when it finally touched down in that infernal landscape? Let's conclude our journey through the thick acidic clouds and arrive at the surface of our closest companion. Earlier, we saw the very first image ever sent from the surface of Venus. Due to the massive clouds of sulfuric acid obscuring any kind of view from space, the only images of Venus that show the surface in visible light are those that have been taken from a lander on the surface. And of those, we only have 6, taken from 4 of the Soviet Venera probes that landed, such as our Venera 7. The air is surprisingly clear. Scientists had wondered whether everything would be obscured by a thick haze, but this doesn't appear to be the case. Everything is a dull yellow, the color of the acidic composition of the atmosphere. And while we might be surprised to find solid, rocky ground under the thick, crushing air of Venus, that ground is also utterly desolate. It hints at ancient lava flows now hardened into flat plains and eroded under Venus's intense atmosphere. Everything seems very dry, which is unsurprising given the baking heat. Perhaps, a billion years into the future, when the sun has increased luminosity enough, we might see similar runaway greenhouse effects and results on Earth. But here, we must leave Venera. The Venera series of probes, including the one whose journey we have been following, never lasted more than a couple of hours on Venus's surface, due to the combination of heat and crushing pressure. Their images give us a brief but vital glimpse into conditions down there on the rocky ground. But although these 40-year-old images are the only cases of photographs being sent from the planet's surface, there is another way we can learn about the geography and topography of Venus. It's not infrared or ultraviolet. Neither infrared nor ultraviolet imaging can break through the thick, cloudy atmosphere to see and map the surface with any kind of clarity. You need something different. Step forward. Radar imaging. Hit the like button, subscribe, and turn on notifications so you won't miss any of our future space journeys. The USSR began the process of using radar to map the surface of Venus with their later Venera models, 15 and 16, in 1983, producing images with a resolution of 1 to 2 kilometers on the ground. This was improved upon roughly a decade later with the NASA Magellan probe, which between 1990 and 1994 managed to map around 98% of the Venusian surface with a resolution of 120 meters. The images produced using the radar data are truly spectacular, revealing colossal volcanic activity, massive cratering, and a surface that is, geologically speaking, reasonably young, possibly as a consequence of the intense volcanic activity, resulting in truly vast lava flows. Do you believe that beneath its deadly crust, this planet once burned like a living heart? If given the chance, would you observe safely from orbit or follow Venera's bold path down to the blazing surface? A composite image of the surface created from data from the Venera, Pioneer, and Magellan missions looks truly spectacular. Surface detail from volcanoes to valleys to craters and chasms shown in clear relief. The remarkable utility of radar imaging to pierce the clouds and show us what lies on the surface of Venus has greatly boosted our knowledge about the planet. And isn't the hidden beauty of it all truly remarkable? So, with all we now know about our nearest planetary neighbor, what remains to be discovered from Venus in the future? The answer is a lot. In recent times, by far the biggest news regarding Venus has been the discovery, or perhaps not, of the gas phosphine high in the Venusian atmosphere. In 2020, measurements from the James Clerk Maxwell telescope indicated the presence of trace amounts of the gas. Phosphine is produced through a variety of different processes, but one of these, and the one that got everyone very excited, is through microbes in a low-oxygen environment? Life in one of the most unlikely, hellish places imaginable? What an outcome that would be. However, subsequent studies found no such phosphine again, and by 2022 the idea of it being present in the Venusian atmosphere had been dismissed by NASA. It would have appeared that the findings of the initial study were in error. But then Professor Jane Greaves of the University of Cardiff went on record at a prestigious meeting in 2023 that the JCMT had found phosphine once again, this time deeper within the atmosphere of Venus. Hopefully, future missions will give us a definitive answer to this truly tantalizing question. Many other questions await answers too. Why, for instance, did two planets, Venus and Earth, so similar in size, evolve so differently? Was there in fact liquid water on the surface once upon a time? What is a more accurate picture of the chemical composition of both the Venusian atmosphere and surface that might help answer these conundrums? After decades of being relatively overlooked in favor of Earth orbit assignments and outer planetary probes, Venus has suddenly garnered interest again. Several missions will be launched for Venus within the next 10 years. What do you think? Are we truly ready to return to the planet once feared, now rediscovered as the solar system's ultimate enigma? These missions originate from the USA, the ESA, Russia, China, India, and even one private American venture, the Venus Life Finder. With any luck, one, more, or all of them will lead us on a voyage of great discovery about our beloved star of the morning and evening, divulging a wealth of information and answering some of our burning questions about Venus. So there we have it all. Looking at Venus through a variety of differing wavelengths has given us far more knowledge than visible light alone could give. We have been able to discern volcano and crater formations through kilometers of opaque clouds, determine some of the chemical composition of both atmosphere and surface, and use infrared imaging to make the invisible visible to us. All of these have granted us precious hints as to why the conditions on it are so extreme. And who knows? Even if it's just the slimmest possibility, there might still be simple microbial life hiding on our closest planetary neighbor. A world once considered the hell of the solar system is now becoming the place that stirs some of the biggest questions about the origins and existence of life beyond Earth. Thank you for staying with us throughout this journey to Venus. From its thick, acidic clouds, to its supersonic winds, down to its scorching surface, and the many scientific mysteries still waiting to be unraveled. If you found this video interesting and informative, don't forget to hit like, subscribe to the channel, and turn on the notification bell so you won't miss our upcoming explorations. Once again, thank you so much, and we'll see you in the next video. What do you think? Could there really be a tiny form of life quietly existing somewhere in those clouds of sulfuric acid, just waiting to be found?